Hello, after studying AC steady-state power, now we can study three-phase circuits. In the beginning, we will study three-phase circuits. We will learn the Y-to-Y configuration and delta-to-delta configurations of three-phase circuits. Afterwards, we will focus on the details of the Y-to-Y configuration, and we will learn 3-wire and 4-wire versions. Afterwards, we will learn how to analyze circuits with Y-to-Y configuration with balanced loads. Indeed, our treatment of the three-phase circuits will be very simple. If you want to study this further, you need to take a course on power transmission systems. A three-phase circuit consists of a three-phase source, a three-phase load, and a transmission line. In the three-phase circuits, the voltages and currents are sinusoids. Therefore, we use the frequency domain representation rather than time domain representation to analyze these circuits. Frequency domain representation using phasors and impedances allow us to use algebraic equations to solve the circuits rather than differential equations. The generation and transmission of electrical power are more efficient in polyphase systems combining 2, 3 or more sinusoidal voltages. Since we generate electrical power using rotational electrical machinery, we end up having sinusoidal voltages generated. Power transmitted by polyphase systems is much smoother, less pulsating compared to single-phase circuits. So basically, we just have much smaller ripple. And also, three-phase AC motors run much smoother than single-phase motors because we have much less torque ripple. The most common form of polyphase systems employs three balanced voltages, equal in magnitude and differing in phase by 120 degrees. An elementary AC generator consists of a rotating magnet and stationary windings A, B, and C, which are on the periphery of the machine. Three sinusoidal voltages VAA, VBB, and VCC are generated on the coils when the magnet is turned with a mechanical torque. That mechanical torque might be due to water in a hydroelectric power station. Let's assume that VAA prime is the potential difference between the terminal A and terminal A prime. Then we can describe the voltages for the three-phase circuit as VAA prime is equal to Vm times cosine omega t. VBB prime is the same voltage with a minus 120 degrees phase. So in other words, Vm times cosine omega t minus 120 degrees. And VCC prime is equal to Vm times cosine omega t minus 240. But we can also write minus 240 as plus 120. So therefore, VCC prime is equal to Vm times cosine omega t plus 120 degrees. A three-phase circuit generates, distributes, and uses energy in the form of three voltages equal in magnitude and symmetric in phase. These three different voltages are called the phases. In this figure, phase A reaches the peak first, followed by phase B and then phase C. So we can tell that the phase rotation is ABC, or the circuit has a positive phase sequence. We can represent using phasors VA, VB, and VC as VA is equal to Vm with 0 degrees, VB is equal to Vm with an angle of minus 120 degrees, and VC is equal to Vm with an angle of 120 degrees. In this specific case with VA, VB, and VC, we call these three voltages balanced since they have the same amplitude Vm and they have the same frequency, and also when we add them together, we end up with 0. In other words, these three vectors VA, VB, and VC added together give us the 0, which means that the voltages are balanced. The three-phase voltage sources can be connected in Y-connected or delta-connected configurations. In the Y-connected configurations, the three sources are connected together at the neutral point, whereas we don't have this neutral point in the delta connected configuration. In this lecture, we will cover the Y-connected sources. At the center of the Y-connected sources, there is a terminal called neutral, abbreviated with small case letter n. In the Y connection, A prime, B prime, and C prime are connected to this neutral terminal. Then the line-to-line voltage VAB of the Y-connected source becomes VA minus VB, and using phasor algebra, we can calculate VAB as square root of 3 times Vm with an angle of 30 degrees. Similarly, we can calculate VBC and VCA. As you can see, the magnitudes of all VAB, VBC, and VCA are square root of 3 Vm, and their angles are still with a phase difference of 120 degrees. Before proceeding further, let us also cover briefly the electrical components associated with three-phase circuits and three-phase voltages. Here you see a three-phase plug. L1, L2, and L3 denote the line voltages, and N is the neutral terminal, and PE stands for the protective earth. The conductor that connects the exposed metallic parts of the consumer's electrical installation is called protective earth, and it is sometimes also called as the protective ground. And the conductor that connects to the start point in the three-phase system, or that carries the return current in a single-phase system, is called the neutral. We should also cover the electrical cable color codes for three-phase circuits. Indeed, for different regions of the world, there are different color codes, but for Kazakhstan, we are using this color code, where line 1 is brown, line 2 is black, line 3 is gray, neutral is blue, and protective earth is yellow and green. So in one-phase circuits, on the other hand, we have the line, which is line 1, as brown and neutral as blue, and protective earth, if it exists, is again yellow and green. In different regions of the world, you might have different type of cable color codes, and it is not guaranteed that these color codes are used for a specific system. However, these are the recommended colors. And as a result, a three-phase cable with protective earth and neutral looks like this. A Y-to-Y circuit consists of three components: a three-phase source here, then a three-phase load consisting of the load impedances ZA, ZB, and ZC, and a transmission line in between. With respect to transmission lines, we have the 4-wire and 3-wire versions. In the 4-wire version, the neutral port of the source is connected to the neutral port of the load. Let us start with the analysis of the 4-wire Y-to-Y circuit. As you can see, the neutral ports of the source and the load are connected to each other, and therefore their potential difference is equal to 0. Therefore, we can utilize these ports as a virtual reference for the circuit and write the current IAA simply as VA over ZA. The current IBB is equal to VB over ZB, and current ICC is equal to VC over ZC. And the current in the wire connecting the neutral node of the source to the neutral node of the load can be given as INN is equal to IA plus IB plus IC, and this is equal to this expression, and therefore we can calculate the average power delivered by the three-phase source to the three-phase load as P is equal to PA plus PB plus PC. Let us continue the analysis of the circuit for the balanced load case. So let us assume that the phase voltages of the Y-connected source are given here. And let us assume that the load is balanced. Load is balanced means that ZA is equal to ZB, which is equal to ZC. And we can just kind of like tell that this is an arbitrary load. It might be an inductive load, it might be a react capacitive load, but it is basically an impedance with an angle. The line currents for the balanced 4-wire circuit are given by this. Vp over Z with an angle of minus theta, and IBV is equal to similarly Vp over Z with an angle of minus theta minus 120 degrees, and for ICC it is given here. And if we add the three currents, we realize that the current flowing from neutral to neutral in the balanced case is equal to 0. So basically, if we have a balanced source and if we have a balanced load, eventually no current flows from the neutral terminal from the load to the neutral terminal of the source. Alright, the voltages are provided here and the currents are provided here for the three different branches of the Y-to-Y circuit. And recalling that for RMS voltages, the average power is given by P is equal to VRMS times IRMS times cosine theta V minus theta I. We can find the average power delivered by the source as PA plus PB plus PC, which is equal to Vp times Vp over Z times cosine minus theta. And we have this term 3 times for all the loads. So accordingly, when we add these and noting that cosine is an even function, so cosine minus theta is equal to cosine theta, we can write P is equal to 3 times Vp squared over Z times cosine theta. This is the average power delivered by the three-phase source, and equal power each is absorbed by each impedance. So the power absorbed by the impedance ZB will be accordingly Vp squared divided by Z times cosine theta. In the case of the 3-wire Y-to-Y circuit, we don't have a connection between the neutral terminal of the source and the neutral terminal of the load. And we need to write the Kirchhoff's current law for the node N by assuming that this neutral terminal of the source is the reference. And accordingly, all the currents entering to this node are IAA, IBB, and ICC, and we can write the Kirchhoff's current law as 0 is equal to VA minus VNN divided by ZA, plus VB minus VNN divided by ZB, plus VC minus VNN divided by ZC, and accordingly, we can find the expression for VNN, the voltage difference between the two neutral ports, as this. So we know all the impedances ZA, ZB, and ZC. We know the VA, VB, and VC as well. And accordingly, we can calculate the numerical value of VNN. And once we find VNN, we can find the phase currents IAA, IBB, and ICC by using these equations. You should remember that for the balanced 3-wire circuit, so when the VA is equal to VB is equal to VC with phase differences, and the load impedances ZA, ZB, and ZC are equal to each other, then VNN is equal to 0, and we don't have to solve the circuit for VNN because we just will have that as 0, and these expressions will simply be, for instance, for the IBB is equal to VB divided by ZB. Alright, in this question, we need to determine the complex power delivered to the three-phase unbalanced. This is the important keyword. So basically, the ZA, ZB, and ZC are different. Unbalanced load of a 4-wire Y-to-Y circuit. The phase voltages are given here as RMS values, and the load impedances are given as ZA, ZB, and ZC. I will start solving this question by finding the phase currents IAA, IBB, and ICC. So IAA is equal to VA divided by ZA, and this will be equal to 220 with an angle of 0 degrees divided by 50 plus J 80 ohms, which is equal to 2.32 with an angle of minus 58 degrees. Similarly, I can find IBB is equal to VB divided by ZB, which is equal to 220 with an angle of minus 120 divided by J50, which is equal to 4.4 with an angle of minus 210, which is equal to 4.4 with an angle of 150 degrees. And similarly, I can find ICC as equal to VC divided by ZC, which is equal to 220 with an angle of 120 degrees divided by 100 plus J25, and this is equal to, if we ask MATLAB what this is, 2.14 with an angle of 106 degrees. After finding these currents, now I can proceed to find the complex power. After calculating the phase currents, we can easily calculate the complex power delivered to the loads. SA will be equal to IAA conjugate times VA, which is equal to 2.32 with an angle of 58 degrees times 220 with an angle of 0 degrees, and according to MATLAB this is equal to 270 plus J 432 volt amperes. Similarly, SB can be calculated as IBB conjugate times VB, which is equal to 4.4 with an angle of minus 150 degrees times 220 with an angle of minus 120 degrees, and this is equal to J 968 volt amperes, and SC similarly is equal to ICC times VC, which is equal to 2.14 with an angle of minus 106 times 220 with an angle of 120 degrees, which is equal to 220, which is equal to, let me see, 456 plus J 114 volt amperes. So I have calculated the complex power delivered to the impedances ZA, ZB, and ZC. Now I can calculate the total complex power delivered to the system as SA plus SB plus SC, and if I add these three, I end up with 726 plus J 1514 volt amperes, and with this I conclude the solution of my problem. Alright, in this question we need to determine the complex power delivered to the three-phase balanced load of a three-wire Y-to-Y circuit. The phase voltages are given here as RMS values, and the balanced load means that ZA is equal to ZB, which is equal to ZC, and the value of the impedances are 50 plus J80. So this makes it much easier to solve this question. Let's find the complex power delivered to the ZA, and for that I will start by finding IAA, which is equal to VA divided by ZA, which is equal to 110 with an angle of 0 divided by 50 plus J80, and according to MATLAB the result is 1.16 with an angle of minus 58 degrees, and the result is ampere as an RMS value. And in order to find the complex power delivered to this load, I will find SA, which is equal to IA conjugate times VA. So IA conjugate is 1.16 with an angle of plus 58. Now times 110 with an angle of 0 degrees, which is equal to 68 plus J 109, and this is in the units of volt amperes. And in a circuit where we just have a balanced source and balanced load, and then I will have S total as 3 times SA. In other words, SB and SC are equal to SA as well, and this will be equal to 204 plus J 327 volt amperes, and this is my final solution. As you can see, when the load impedances are balanced, it is much easier to solve the question.